when you go to the World Wide Web, and then especially to a very popular website that is called worldradiohistory.com, you can find all kinds of books from the 1920s, 1970s, 1980s, and there are also very interesting circuits that were published in the past, in the 1980s, by Elektor. Elektor in the Netherlands. And as far as I know, they also published in not only in the Dutch language, but also in the English language. Anyway, I found on that website this circuit. It is a capacitor tester, and I want to refer to my earlier video, and I will give a link in the text box, where I thought that I was working on an electrolytic capacitor tester. And this circuit is made with a 555 chip. That's a well-known timer chip. It's used for all kinds of purposes, and here you see it. It's on the breadboard in a certain way, but I'm going to make this circuit also in a definite way. So here is the original schematic. So like I found it on World Radio History, you can find it when you want to study that. Elektor 301 circuits 178. The author was Bouman, G. Bouman, so credits to G. Bouman about this circuit. It is a very, very good working circuit. This is how it was published, and well, of course, I had to say encrypt that in a certain way, and here you see how I encrypted it. Say in the way that I publish my circuits, and also important that in the original circuit there was, say, there was a 5 voltage supply, but of course when we are talking about measurement instruments, that 5 volt has to be stabilized. And that's the reason why I made this circuit this way. So I adapted it a little bit, and I made it in a way that I always make my circuits, say soldering here this 555 to the board with brass nails, etc, etc. And here is the 5 volt regulator. It's supplied by 9 up to 12 volts. There are two capacitors here of 0.1 microfarad, and here is an extra capacitor of 0.82 microfarad that bridges in fact this capacitor. This is the input of the 7805 voltage regulator, and here the output. Input also a capacitor of 47 microfarad. The interesting thing was that in the original schematic there were two ranges. When this resistor RA and RB, by the way, also this, were respectively 1K and 220 ohms, it could measure in the to the maximum 1000 microfarad range, and when RA here is 1 mega ohm and RB is 220K, 220,000 ohms, the range is 1 microfarad maximum. So you can test that, you could do an experiment, no problem with that, always good. And here I've used a output capacitor of 100 nanofarad. That is 0.1 microfarad. So let's see what this circuit can bring. Like I told, I have tested all these capacitors. I was very surprised that it even could measure capacitors in the, say the lowest value that I tested was 100 picofarad. So from 100 picofarad to 100 microfarad. That's a big range. Say in the order of 10,000, perhaps 100,000 anyway. Picofarad and microfarad. That's an enormous difference. So here we have the capacitor under test. That's now here. It's that 100 picofarad capacitor. And you can see on the scope that even with that 100 picofarad capacitor there is a kind of oscillation. There's a real oscillation. And it's on 420 kilohertz. So I put down the camera for a while and I now will show this capacitor 10 nanofarad. And of course we have seen that the oscillation on the screen was not very proper, and then I mean it looked like a kind of peak, but here we are on 10 nanofarad. This is a quite good, say, square wave, and it is on 38 kilohertz. And of course when you want to use this circuit, make a table for yourself and say find reliable capacitors with say a low tolerance, and then measure them and make a table for yourself about the frequency that such a capacitor generates in this typical 555 timer circuit. That's important. And you can also see very big differences. You can surely see when a capacitor has a tolerance of 20%. That is sometimes the case anyway. So now I want to show the table with all the, say, different frequencies that are generated by the this oscillator, square wave oscillator. This is a 100 nanofarad capacitor. This one, let's see what it can bring. Well, I have to say, you always say, switch the oscilloscope and the frequency counter a little bit. You see a straight line and think it doesn't oscillate, but of course it oscillates. This is 100 nanofarad, so 0.1 microfarad, oscillates on 4 kilohertz approximately. So here's the table that I made. I've tested this whole bunch of capacitors, and in fact this circuit is extremely easy to make and gives reliable results. So here are here's the table of the say the frequencies generated with this 555 timer chip. 100 picofarad is 440 kilocycles. Of course, is this a very precise figure? Well, you have to study that. Say test 4 capacitors of 100 picofarad and then read out. And the same applies to all the other capacitors. 1 and 5, 1500 picofarad, 130 kilocycles. 15 nanofarad, 27 kilocycles. 47 nanofarad, 10.4 kilocycles. 100 nanofarad, 0.1 kilocycles, and it can also test electrolytics. This was a non-polar capacitor, by the way. It was approximately 420 Hz, 10 microfarad electrolytic with 45 Hz, 33 microfarad electrolytic 13 Hz, 100 microfarad 5 Hz. Well, perhaps it's interesting to show that final value, 100 microfarad, especially on scope. That's of course always interesting. And as far as I could see, it doesn't matter how you connect the cap to the tester, this tester. And here we have the frequency on, that's 5 Hz approximately on 100 microfarad. So 5 Hz. 100 microfarad is 5 Hz. I did not go to higher electrolytic capacitor values. Surely you can do that experiment, say 220 microfarad, perhaps even 1000 microfarad. I didn't test it, but it's a completely properly working circuit with, say, a lot of promises. Thanks for watching. I had not expected that this could work so good. Schematic again, when I can find it. Well, anyway, this is the schematic again, the schematic how I made it. Thanks for watching.